Example 5. Methyl hydrazine is used as a liquid rocket fuel. The combustion of methyl hydrazine with oxygen produces nitrogen gas, carbon dioxide gas, and water liquid. When 4.00 gram of methyl hydrazine is combusted in a bomb calorimeter, the temperature of the calorimeter increases from 25.00 degrees Celsius to 39.50 degrees Celsius. In a separate experiment, the heat capacity of the calorimeter is measured to be 7.795 kilojoule per degree Celsius. Calculate the heat of reaction for the combustion of a mole of methyl hydrazine. As we always do, the first step is to summarize the most important information. The most important information includes numbers with units, what we are looking for, and balanced chemical equations if there are chemical reactions in the problem. For a heat calculation problem, I recommend you to use a 2-column worksheet to summarize the most important information. In a heat calculation problem, temperatures always belong to a physical process. The heat capacity always belongs to a physical process as well. A chemical reaction always belongs to a chemical process. There is another thing you have to pay special attention. Delta H reaction is always directly behind the balanced chemical equation. Below delta H reaction, it has to be the heat. Because this is a process 2, we call this Q2. Even if we don't know the value of Q2, we still put Q2 directly below delta H reaction. Now let's start from the physical process first. Since we are given the heat capacity, the initial temperature, and the final temperature. Since we only have 3 equations to calculate the heat of a physical process, it seems the third equation will be our best choice. We already know the value of the heat capacity. We don't know delta T, but we know the initial temperature and the final temperature. We can calculate delta T. Well, if we know the values of the heat capacity and delta T, we can calculate Q1. There is another hidden information for almost all calorimetry calculations, which is Q1 equal to negative Q2, which means the heat released by one process must be equal to the heat absorbed by another process, because absorbing heat is positive, released heat is negative. That's why we add a negative sign before Q2. You can also write down Q2 equal to negative Q1 or negative Q1 equal to Q2. These two equations are the same. Well, since we already know the value of Q1, we can plug into this equation to get the value of Q2. If you want, you can show your work right now. Well, from this equation, we can get the value of Q2. Since we know the value of Q2, we can put the value of Q2 here. Now let's look at what we are looking for and what we are given. You are given a balanced chemical equation, and you know the mass of one reactant. If you treat delta H reaction as one of the products, you know the value of Q2. This is a stoichiometry type of calculation, which we already know in chapter 3. So what I'm going to do is I'm going to show you the answer directly. Well, for stoichiometry calculations, since we are given the mass of one reactant, we have to calculate the molar mass of this reactant. I converted this number into scientific notation because the answer needs to have 3 significant figures from our calculation. It seems this should be the final answer. However, when you read the problem Actually, we need to calculate the heat of reaction for the combustion of a mole of methyl hydrazine. But from the chemical equation, actually, this delta H reaction is for 2 moles of methyl hydrazine. Therefore, our final answer should be this value divided by 2.